Okay, so we just finished the lab for EFA. So we're trying to find the 4 cognitive abilities from 19 tests. And then we move forward to CFA. So we talk about these topics. How to conduct CFA, model identification, evaluation, and we have an example, okay, using the R code and M+ code. We use Laverne instead of SEM. So last semester, when I introduced the software of the SEM, we use SEM, okay, the package of SEM, because it's very simple for us to understand the meaning of each statement. So we have different parameter names and the meanings and the starting values. And now we use the Laverne package to kind of like simplify this whole procedure. Okay. And today we're gonna cover more topics about CFA. Okay, so actually it's kind of like a review and some other related issues. For example, the patterns. We actually look at the patterns of vector structures. And then we can have a review again. And we're going to look at the covariance of correlation relationship. Okay, so we use a correlation matrix to do the decomposition, but actually for covariance, we can transfer the two correlations by using a very simple formula. And then we're going to go back to look at the communalities. Okay, we mentioned the communalities. And we will have the example. Yeah, we're going to look at the old example again. How did we get this communication? Correlations. And we also will look at some hybrid cases. So that those are not good cases. So sometimes in practical, you may have these cases. Theoretically, it's good, but practically, you may have different error message. And then, how are we going to handle those cases? Okay, so I can provide you some suggestions and also number of factors. And this part is still young, so we cannot see anything. In section 2, we're gonna move forward we're gonna look at the higher order factor analysis. So far, we just look at the first order factor analysis. We can have second order or third order or higher order. And then we will have different techniques of factor analysis. Okay, for example, P technique, or Q technique, R technique. You want to stay here. Okay, so factor analysis. In general, we have 2 branches, EFA and CFA. So those are steps for EFA, and these are steps for CFA. Okay, so we have to specify a factor model. Okay, what are your factors? What are your indicators? So what are those loadings? So specify. So give a specific definition of your factor model. And then you need to identify your model, identify the factor models. And then run CFA. And after you got the result, you're going to evaluate the model fit. Is that good or not? Okay. And then you also need to do some interpretation. Why we have, those fact loadings. So what does that mean? So do the interpretations. So let's look at the related issues. Okay. So first, actually, we have already covered this part in last week. Fact loadings. Okay, so this is the EFA result. So all of these space are filled out numbers. So there are no empty space. Okay, so all of these are numbers, but these are small numbers, so that our code just delete those small numbers, but actually they are there. So that is an estimate of the parameters of factor loadings, called factor loadings. But still, we have some small numbers. We use a gray color to mark them. So these numbers actually can be deleted if you really want to keep a simple structure of the factor loading. So these numbers are too small, 0.1 something, okay, 0.2 something. But the larger numbers indicate there are strong relationship between the factor and the indicators, so that we might keep them. So after we delete those gray colored loadings, we have very, very clear factor structure. So that's how you can do the EFA. Okay, this is for factor structure. Yeah, those are names. And by looking at these names of the indicators, you give a name of those factors. Summarize many of indicators we test. We have 4 latent factors named. Okay, then model identification. As I mentioned, okay, so by looking at the observed Y, you have latent factor loadings. Lambdas are all unknown. Factor scores are all unknown. If you don't identify something, if you do not fix something, there's no unique solutions, because there are so many possibilities to get the same answer. So we have to fix something that we call the model identification. So in factor models, this part, So we either fix a non-zero loading at 1. So the unit of the factors will be fixed. So what does that mean? So if I fix a 1 non-zero loading at 1, that means if I change 1 unit in the latent factor, the observed not latent indicator will have the same change. That's the meaning of the factor loading equals 1. So you kind of like keep the scale as that indicator to fix that unknown, unobserved latent part. That's one method, identify model. We can also fix the variance of the latent factor at 1. This is another way to identify our model so that we can have the estimate of factor loadings. So either fix the factor loading or fix the variance of latent factor. Okay. By using this, we can have the solutions. Otherwise, there's no estimates. And by default, so in M plus or in R or Immerse or other factor software, if you don't do anything, the computer will do the model identification for you, because by default, they will do something. But that doesn't mean that you didn't identify your model. Actually, you did that, but the computer has already done that for you. So you need to check the default setting, because by different notation, by different options or different software, they may have different method. And then we look at rotations. Okay, so rotations will have different ways. Okay, rotations just put the axis and the y axis freely. So trying to get a better understanding or interpretation of those factors. So you can use orthogonal rotation, or you can use oblique. This is oblique. This is also oblique rotations. Okay, and this is orthogonal. Okay. This is non-rotated method. So in this case, those factors are not very, here we assume there are 2 factors. These 2 factors are not very convenient for us to do the interpretation. So if we have these 2 rotations, then it makes sense. Okay, those observed y values are influenced by factor 1 only. Okay, and those observed variables are influenced by factor 2 only. So in that way, we can clearly understand what's the meaning of factor 1, what's the meaning of factor 2. Of course, you can also do that, but the interpretation will not be so obvious. You have to say that, okay, so for these variables, largely influenced by factor 2, but also influenced by factor 1, partially influenced by factor 1. So it's not very easy for us to understand those factors. And these variables largely influenced by factor 1, but sometimes it's also influenced by factor 2. So that's another good way. So we better to do this rotation. And the same thing here, okay? So the only goal to do the rotation is just provide a better interpretation of factors. So that's it, okay? And then let's look at the relationship between covariance matrix and the correlation matrix. So last lesson, or including this method, the beginning of this method, we make a lot of efforts to try to derive the covariance matrix, But when we do the correlation, or not, when we do the EFA, we actually mainly focus on the correlation. Okay? Correlation matrix, suppose it's P. So what's the relationship between the covariance matrix, capital sigma, and the correlation matrix P? That is a transformation. Okay, suppose we have covariance matrix and the diagonal elements. Okay, we take out all the diagonal elements without the off-diagonal elements. We call it D. Then the correlation equals this format. Okay, the covariance matrix here times pre-multiplied by the D matrix. The D matrix is defined here, and the square root of the negative square root of these elements, and also post the multiplication of this capital sigma matrix. But then it is actually this is square root of all the diagonal elements of the D for the covariance matrix. So although we did the decomposition, eigen decomposition based on P, but actually because of the close relationship between the sigma and the P, we can do a simple transformation to get the relationship, to get the decomposition of sigma. Okay, so if we have a detailed example, I'll show you this. Okay, so suppose we have capital sigma, we have a bunch of diagonal elements. For example, I have A, B, C, D, and off diagonal elements. Okay, so we have some numbers. Okay. And then the D actually is just the diagonal of the capital sigma. So it is A, B, C, D. And all of these are 0, 0. That is D. So how to get the correlation matrix of the capital sigma covariance matrix? P equals, okay, the diagonal elements, negative square root capital sigma D, negative square root. So we have the whole matrix here. Oh, this is green. Let me just write it here. It's too bright. So we have the whole matrix sigma here. A, B, C, D. And we have some. So we can just do the D square root inverse. Okay, so we have like this. Okay. And all of these are 0, 0, okay? This is the left part. And we also have the right part. And do the matrix multiplication. Matrix do the multiplication. We can check the diagonal elements here. Okay, we have A, B, C, D here. And we have this part and this part. If you think about the matrix rule, matrix algebra rule, so left side, right side, middle, and it's diagonal, we can just cancel all of these elements, okay? Because it's just one. So the diagonal elements is just 1, 1, 1, 1. Okay? We have left side, that means a row multiplication, column multiplication, this. But when you look at these off diagonal elements, okay, all of these will do the divide by either this one or this one or this one, this one. After you do the matrix algebra, all of these are just like, suppose this is the original, this is E, and it will be E divided by square root A and the square root of B, something like that. And we have F here, that's F divided by square root of A, square root of C. So you do the calculation continually. So what are these? These are just correlation. Okay, covariance divided by the standard deviation. This is a variance, standard deviation of A, standard deviation of B. So this is just correlation between A and B. This is just correlation between A and C. Okay, all of these are correlations. That's why the whole matrix is just correlation matrix. Okay, these are correlations. And these are 1, 1, 1, 1. So this is a correlation matrix. So by using this formula, we have the correlation matrix derived from the covariance matrix. Yeah, so this is a detailed explanation of this formula. Good. Yeah, so the correlation is related to a covariance divided by the square root of variance of specific corresponding variables. Okay, standard deviation of the variables involved. And also we can look at this. This is kind of like a its transformation. So we try to have a new version of the correlation matrix. Suppose this is the P, original P, okay? So we have this formula, we got it from the previous slides. And what is a covariance matrix? Based on the factor model, remember we have formula for this covariance matrix. So this is our formula. I'm sorry, so this is very hard to tell. Maybe next time we can move to the other. This is not good. Okay, so
yes, ma'am.
Next week we're gonna use the 207. Okay, so we have the correlation matrix here. And then what is the covariance matrix? Take the symbol. Remember that, okay, we have F lambda F plus B. This is a factor model. Okay, this is a factor model. When we try to get the variance of this factor, I'm sorry, this is 1, observe 1. This is when we try to get the covariance matrix, which is the covariance matrix of the Y. So we have the matrix form. What is the matrix form? It is Y lambda F plus epsilon. And this becomes capital sigma. We have lambda times variance of F, which is phi. Okay, we use phi to show it. Transpose of lambda psi. Okay. So we just replace the capital sigma by using this form. So we have this covariance matrix of the sigma, okay? And then we do the derivation. So we have left side, we have right side. Start. Just separate these two parts because we have class here. So separate these two parts and then do the derivation. So we have the left side here, have the right side here. This is very complicated. And then look at this part. Okay, so we try to combine these two matrices together. So we have the diagonal matrix next square root, okay, of these elements of these diagonal elements times lambda. If we have these two combined, then this is just a transpose of these four matrices. So this is one combination. So this is just transpose of the same calculation because this follows a transpose rule. Okay, remember the transpose of the product of two matrices is the product of two transformed matrices. Okay, but this is diagonal. Diagonal transpose is a set. It's itself. So this is just this one transpose. Okay, and then we can rename it. We can rename this matrix as new factor loading. This is our new factor loading. So this is our original factor loading. So this is original factor loading. And using this way, we have a new factor loading. Okay, lambda star. But still, we have this form. Okay, we also do the transformation. So we have new factor loading, and the phi is the same phi. And the lambda is a new factor loading. Okay, new factor lambda, no lambda transpose. And then we have the new side. This is a new side. Okay, B, and the original side here, and the B. Okay. This is a new side. So we have new lambda here, new side here. So when you do the calculation, it is still have a sigma. So sigma can have this form, sigma can have another this form. The only difference is here. Okay, so we have lambda or the traditional lambda or the older lambda here. We have the diagonal element matrix pre-multiplied by this matrix. Then we have form. But look at this form, okay? This is a correlation, okay? This is a correlation. Originally, this form is for the covariance matrix, okay? Covariance matrix is for the original lambda. If we use a correlation matrix, we have the new lambda, new psi. So the correlation have also this form. So this is another relationship between this P and T. Okay. So what does that mean? Why do we want to do this? This tells us the covariance matrix can also have the similar pattern, the EFA. Okay. So if we have this form, then the correlation matrix is just the covariance matrix. Okay, if we have this new number. So if you do the decomposition of the correlation matrix, P, you can also do the eigen decomposition based on the sigma. Actually, this is a sigma. Okay. Yeah, so the capital sigma covariance matrix and the correlation matrix is closely related. So if you want to do the covariance decomposition, it's totally fine. Okay, you just derive the formula here. So the P must also use covariance form. I only needed to do the elevated transformation. Okay. The factor loading for the correlation structure is new part, the new factor loading lambda are equivalent to the factor loadings for the covariant structure, each divided by the standard deviation of the corresponding manifest variables. And that's a common factors part. Common factors part. For the unique factors, for the psi part, we also have this relationship. Okay. So for the psi part, unique variances for the correlation matrix psi star, mu psi, are equivalent to the unique variance for the covariance structure, each divided by the covariance, each divided by the variance of the corresponding manifest variables. Okay. This is a mu psi. This is mu psi. Okay. So that's for covariance matrix, sigma and p. Okay. And if we assume, okay, here, if we assume the phi is identity matrix, what does that mean? So if we assume all the factors are independent, orthogonal, then this phi is just identity matrix. Okay, so we have this form. We don't have the phi here because the phi is identity matrix. So we have this simplified matrix, but this is only for uncorrelated independent factors. For oblique factors or not orthogonal factors, we cannot just delete this phi here. And the lambda star and the psi star is still has the same form here. Okay, the lambda star is this star. The psi star is this star. Okay. It's not involved phi. This part is independent with phi. Okay, now let's focus on this part. If we have this part, let's do the calculation. Now you have a communality and a correlation. So everything comes from this format, this formula. Okay, so lambda, suppose all the lambda elements inside of the lambda here like this. Suppose this is a lambda 1, 1, okay. Lambda 1, 2. Lambda 1, 3. Lambda 1, 4. Suppose we have 4, okay, factors. So we have 2, 1. 2, 2. 2, 3. So this is a lambda. Then lambda times the transpose of the lambda. Transpose of lambda. Okay, just transpose. Okay, the row here becomes column here. We have lambda 1, 1. We have lambda 1, 2. Lambda 1, 3. Lambda 1, 4. The column, okay, the rows becomes column, and the row here becomes a column here. Lambda 2, 1. Lambda 2, 2. Lambda 2, 3. Lambda 2, 4. This is the third column, the fourth column. Okay, then do the multiplication. So lambda times transpose of the lambda. Okay. This is the correlation P equal this time this and plus psi. We also have psi. Psi 1, 1, psi 2, 2. 533, 544. Okay, just do the calculation. Just do the calculation. And then we have a bunch of numbers here. Okay, so. Oh, wait a minute. This is, I'm sorry, this is a P by K. I'm sorry. So we should continue. I'm sorry. So we should, this is P, number of variables. Okay, this is P. Suppose we have 19 tests. Okay, we have 4 vectors. So we have 19 tests. And the P is 19 by 19. Okay, P by P. I'm sorry. This is P. This is a number of variables. So this P means, okay, correlation matrix. This is a dimension. And now we have P. Sorry. And here's her. P by P. This is 4 by P. 4 by P. This is P by 4. Okay, then just do the multiplication. So this part, this is also P by P. Okay. This is then the product of this area is P by P. Okay. So what's the diagonal elements? So let's look at the first element. These first row, first column. So the diagonal elements on the first position, it is the first row here, first column here. What is that? It's lambda 1 1 6. Okay, it's the same elements here. Lambda 1 2 okay, plus lambda 1 2 6. Lambda 1 3 okay. Lambda 1 3 6. Lambda 1 4 6. This is only its first element in the main diagonal element of the product. Okay. This is 19 by 19, suppose. Okay, so we have so many. This is first element here. We have second element. We have all of these elements. Big matrix. Okay. The second row, second column. It's the same thing. Okay. Second row, second. So this element squared plus this element squared. Okay, plus element squared plus element squared. That's the main diagonal elements of this product. What are these numbers? These are communalities. Okay. Yeah. This is a left side. Okay, suppose case 4, then we have 1 4 squared. So this is the main diagonal elements. And we also have the unique variance here, plus all of these diagonal elements and plus the diagonal elements here. It's correlation. It's 1. It's 1. So the first element and the diagonal of the correlation P, 1 equals the left side of the coming from the common factors, and the right side coming from the unique factors. Okay, add them together, we have 1, and we call the left side of this area coming from the common factors communality. Okay, this is the communality of the first element, 1. And of course, we have the unique variance. Psi 1, 1. And continue, we have row 2, 2 over here. 2, 2. The second row here, second column here, squared, element squared, element squared, element. Suppose we have K. Then this is lambda 2, 1 squared, okay, 2, 2 squared, 2, 2, 2K squared. Again, this part is called communality of the second variable. And of course, we have the unique variance side. So you do all the calculation, we just have all these decomposition. Decomposition of two parts. Okay, the correlation matrix into two parts. The communality part and the unique variance part. Yeah, the sum of squared factor loadings. All of these are factor loadings. Okay, all of these are factor loadings. Lambda, 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 all of these. So suppose we have P by K, okay? P by K, these are factor loadings. The squared factor loadings plus the unique variance is 1. Okay, it's a one element or component of the correlation. So that's why we have the communality calculation. I think in the very beginning, we have this slide. This is a review slide. Okay, I said the communality for the G's variable, often denoted by the H, okay, and how to calculate the H. It is a sum, okay, it is a sum of the squared factor loadings for all factors for the G's variable, okay. It's a sum of squared factor loadings for all common factors. So that is called the H communality. And the total communality for common factors is the sum of all of these diagonal elements. That's the total thing. But for each variable, we have one communality. And how to get the psi? Here we said, okay, psi is 1 minus the communality. Why do we have 1 minus communality? Because of this calculation. Because of here, okay? If you know this part, 1 minus this part is a unique variance side here, okay? So the sum of these two is 1. So that's why when we have the communality slide, I said the psi is 1 minus 3. So at that time, I didn't talk about these factor loadings because they're gonna confuse you. We don't know the logic here. But now we understand the covariance matrix of capital sigma and P. We know the relationship. We can do the calculation, so we understand the logic here. Okay. So that's why we have the communality, and this is example. We have, suppose in this case, we have 4 variables. We have 2 vectors. So I ask you how to get the communality of the first variable, how to get the communality of the second or third or fourth variable. You only need to get the squared value of the factor loading plus the squared value of this factor loading. But at that time, why? We don't know. But now, you should understand why do we have that formula. Okay, it's 0.4, it's a 0.7 squared. Okay, it's 0.49 plus 0.01, it's 0.5. So 0.5 is a communality of the first observed variable. And the sum of this is a 0.49 is a communality for the second variable. And the sum of the squared of these two elements is 0.5 is a communality of the third variable. And here we have 0.72 is the communality for the first variable, okay? And for the psi, once you get all the communalities, just 1 minus that communality, you have the psi element. So you have psi 1, psi 2, psi 3, psi 4. Okay. Yeah. So this is a recover. This is a review part of the communality. At that time, we said, okay, we're going to come back to this topic again. We're going to explain why do we have that calculation here. So this is the reason, okay? This is the reason. This is the reason. Everything coming from here, okay? Okay, so that's a diagonal element. Not okay. We didn't finish that yet. We just covered the diagonal elements. That's diagonal elements. But how about these off-diagonal elements? What are these? It's a correlation matrix. Okay, the diagonal elements is 1. But how about these off-diagonal elements? These are correlations among different variables. How are we going to get those correlations based on our factor loadings? We can directly get those correlations from our factor loading matrix. How? Okay, that's the second step to check the off-diagonal elements. Yeah, those are off-diagonal elements. Same thing, you do the calculation, you just continue to do the calculation. Okay, there's a huge lambda here. Transpose of the huge lambda here. And do the calculation. Okay, the first row, second column is a correlation between 1 and 2. Okay, the product of these two, okay, the vectors, we have two vectors. The product of these two vectors is the correlation between first variable and the second variable, okay? So 1 here, 2 here. And of course, here, this is 0. Off diagonal elements, we don't have anything. So 0. Then all of these is just correlation. Correlation between first variable and second variable, okay? It's just the two vectors multiplication, the product. And the correlation between 2, 3. It's a product of two vectors. Okay. 2 and 3. Okay. The second column, or second row here, second row, and the third row. And the 2, 1 is a second row. Okay. First row. Okay. All of these are correlations. So we have a lot of correlations, which can be shown by our correlation. Factor loading, calculated by our factor loading number. So correlation into manifest variables equal to the sum of products of factor loadings for these two variables. Okay, common factors. And the unique variance do not contribute to explain correlations because we assume that numbers are 0, 0, 0, so we don't have anything contributed to the common factors accounted for the correlations among the manifest variables. Okay, only common factors accounted for by the correlations. And here, okay, so if two manifest variables have high loadings on one or more of the same factors, so if you look at this lambda, if some lambdas are very high, okay, these are factor loadings. If some lambdas are quite high, and then when you do the multiplication and the sum, the correlation will be high. Because correlation is a function of this factor loadings. Okay. If two manifest variables do not load highly on any of the same factors, the sum of product loadings will be low. If all the factor loadings are tiny, small, if we do the sum of this product, it's still low. Because, okay, it's loading, okay, so this is a really low loadings according for the correlation. So if all of these loadings are low, then the correlation will be low. If the correlation is high, then somewhere on these factor loadings will be high. Okay. Okay. And yeah, this is the same example. So we just use this example to do the communality calculation. We can also use this example to calculate the correlation. Okay, for example, based on this lambda here, okay, just we have this lambda values. What is the correlation between V1 and V2? Okay, so we have 4 variables. V1, V2, V3, V4. based on the factor loadings here, what is the correlation between V1 and V2? Oh, here, this is a 4. So just look at this case. If we look at the formula, that's a formula, okay? That's a formula. So how do you calculate the correlation between V1 and V2? So how do you calculate the correlation? Yeah. V1, V2, okay. So correlation between 1 and 2. Correlation between 1 and 2. So how do you calculate that? The lambda, okay, so we have these two lambda. 2, we have these two lambdas. So you only need to do the calculation like this, okay, so lambda 7 point times lambda 21.7 plus 0.1 times 0. This is 0. And then we have 0.49. This is the correlation between variable 1 and variable 2. Okay. What is the correlation between V1 and V3? So it's 1, 3. 1, 3. The first row of the factor loadings, 0.7.1. Okay. The third row, 0.1.7. So 0.7 times 0.1 plus 0.1 times 0.7. 0.14. Okay. Yeah. This is the correlation between 1 and 3. So let's look at these two cases. Okay. So variable 1 is influenced strongly by factor 1 because the factor loading is 0.7. It's really high. So that means variable 1 is strongly influenced by this factor. But look at variable 3. Variable 3 is strongly influenced by factor 2, not factor 1. So these two are not so correlated. So if you check the correlation, it's quite small because these two variables are influenced by different factors. This is influenced by factor 1, this is influenced by factor 2. These are different factors. So the correlation should be low. Should be low. So that's why we have very low correlation, only 0.14. But when you look at factor, I'm sorry, not factor, variable 1, variable 2, variable 1 strongly influenced by factor 1, 0.7, the factor loading here. Variable 2 strongly influenced by factor 1 also. So when you check the correlation of these two variables, it's 0.9, it's quite large because these two variables are influenced by the same factor, factor 1, by the same factor. It's common factors, okay. So that's why these two variables, variable 1 and variable 2, have very high correlation, almost 0.5, okay, but not for variable 1 and variable 3. Okay. These are influenced by different factors. So the correlation should be very slow, okay, just like this case. So that explains the correlation and the factor loadings are, okay, really correlated. Any question? Okay. Then let's look at some really bad cases. These are called bad cases. You don't want to meet them, okay? So let's look at the commonalities. So we have the commonalities. Okay, commonalities we calculated here. These are commonalities. Okay. These are commonalities. This is a variance. All of these are squared. Okay, positive part, and it's 1. So in theoretically, the commonality cannot be larger than 1. If it's larger than 1, it's it's nonsense because theoretically it could not have those cases. But in reality, when you access computer do the calculation, sometimes because the algorithm, a lot of reasons, the commonality, the estimate, okay, not the theoretical value, the estimate maybe is higher than 1. Okay, if it's 1, that situation is called a Haywood case. If it's larger than 1, it's called ultra Haywood case. Ultra Haywood cases. Okay. So if you have this case, if the variance of the commonality or the commonality of variable is larger than 1, let's check this equation again. Here. If suppose this part is larger than 1, but the sum should be 1 because it's a correlation. What does that mean? The unique variance should be negative. So what does that mean? So the variance of the unique factor is negative. That does not make any sense. This is a ultra Haywood cases. Okay.
So this ultra Haywood terminology, is this something that is commonly used if we were writing it as a part of our analysis?
Not common. It's not common.
Is it only in SEM?
But it will happen.
Okay.
In those cases, I will give you some reasons. So you may have different reasons to have the Haywood cases or ultra Haywood cases.
Sure. Thank you.
Yeah. Yeah, so we may have different very bad cases. In that case, okay, sometimes when you do the M plus or any kind of like analysis, you may have negative variance part. The variance of the residual or the variance factors of sometimes, okay, why the variance is negative? Because something wrong here, okay? Because of something it's not ideal cases. Why? Okay. Why do we have those very bad cases? Sometimes your data are not so normally distributed. You have a lot of outliers. Okay? Outliers can cause Haywood cases. And if you choose different or very bad starting values, okay, so we have a lot of algorithm. In some cases, so they allow you to choose different starting values. If you choose bad starting values, when I do the convert, so we just convert to really bad cases. Okay. And also, it may due to number of common factors. If you have too many common factors, or if you have too few common factors, you might have these cases. Okay. Okay. So the number of factors will influence the estimated result. And it may due to small sample size, okay? Not enough data to provide a stable estimate. So that's why always, okay, the larger sample size, the better. The larger N, the better. If your budget allows, so always collect more data, okay, to make your data robust. So if the sample size is too small, you may have like these cases. Sometimes you need to misspecify the model. So you have your data here. We assume that, okay, we're gonna try this vector model, but if the model is wrong, the misspecified, so they're trying to you trying to fit a wrong model with this data set. Then it's yeah. So the match is not so good. So we may have hidden cases, or when you have unidentified and identification models, and sometimes, okay, it's not convergence for some other reasons, all of these reasons, so it may due to a lot of reasons, you have this Haywood case or ultra Haywood cases. So how are we going to handle these cases? So these are some suggestions I provide, and I cannot guarantee that these gonna solve your problem. I don't know. Okay, but you can try different solutions. You can change your starting values. Okay. change the starting values to some practical starting values or very reasonable values. You can just have a start guess. Okay, you can have an initial guess. What are these solutions? Just give a reasonable starting values. You can also try to use different estimation methods. Okay, so there will be some options for you. What is the estimation method? You can try different estimation methods. Collect more data. Okay, so make your sample size large, make your N very large. Constrain or modify your model. So if your model actually is not so reasonable, you can just try to modify it. Okay, try to add something or delete something, put some constraint on some values, try to change your model a little bit. And of course, you have some other remedies to this solution, to these cases. So that's just my suggestion. Okay, so we covered the HIP cases, and then this is a last topic. Okay, so we're gonna cover for session 1. How to choose a number of factors. We learned a lot of methods. Okay, we have a lot of rules and methods. But before you do the analysis, you can just guess. Okay, you can consider prior hypothesis about the number of factors. So when you have a data set, when you have design, so initially you should have some rough guess. Okay, how many factors will you have?
Factors would be like the questions for each construct, correct?
Factors are the two unknown variables you're trying to measure, but you cannot get it. So you have to borrow some indicators for the test. Okay, yeah, some unknown quantities. Yeah. And yeah, so you can also do the eigen decomposition. So use for example, the Kaiser's rule, okay, cumulative eigenvalues, or the split plot to try to figure out the number of factors, and the parallel analysis to figure out what is this K. And after you decide the K, you have to look at the measure of the test. Okay, look at the model fit. Okay, if the model fit is not good, then you can try other number of factors. Of course, you can do a lot of rotations. Okay, rotations. If you have m factors, okay, so if you decide with m factors, then you can compare it with n-1 factor model or n+1 factor models. We just change the number of factors to see which model fits your data best. Okay? So if it is significantly worse, if you use a smaller number of factors, or if it's significantly better, if you have more factor models. So finally, you have a decision. That decision is up to you. You decide what is the number of factors. Okay? But that decisions have to be a combination of interpretability and model fit and parsimony. Okay, so you have your data, you have your theory, you have your model fit. Just combine all of this, okay, and the interpretation of your model. And then you find a balance. Okay, you find a balance among all of these, and you decide the number of factors. Okay, I think that covers our EFA and CFA, some issues, okay, some related issues. So you have homework for EFA. This is your homework 3. Okay. I will upload a data file called risk W VLC, and in that variable, in that data set, there are 13 tests. Okay, information test, similarity test, arithmetic test, vocabulary tests. So in total, you have 13 tests. And the data actually is very famous or very traditional. It's coming from Westler Intelligence Scale for Children. So it's called the risk. Okay, third stage. And based on that data set, I would like you to conduct an EFA, trying to figure out what's the factor pattern. Okay, so you need to decide number of factors. You can use all of this method. Just use these slides and the information I provided here. You can choose Kaiser or you can use parallel, it doesn't matter. But you can use a theory report. Okay, so but when you decide that, hey, please let me know why. Okay, please just show me. Okay, why do you want to choose K? K is 2 or 3 or 4 or 5. Why? Okay, what method do you use? Okay, did you use? And based on the estimated factor notice, what is the factor structure? So finally, you need to provide this part for me. Okay. What is a factor structure? You may have some cross loadings. If these two numbers are really large, you can just leave it here. So, but show me the structure. Show me the factor loading structure, the patterns. Yeah.
Should this be an output from one of the softwares, or is this something manually built?
Yeah, it's from R.
Okay, thank you.
But this is not okay. This is from R. After some notations, I decided to use this matrix, but I also deleted some numbers here. Yeah.
Okay.
Yeah. So that's the second step. Okay, first step, what is the K, why, and how? Okay. Second step, what is the factor structure? And how are you going to do the interpretation or name those factors? So that means you have to give a name for all of these factors. For example, okay, so these, I think these are kind of like a speed test. Or you can just think about it. Calculation ability or math ability, something like that. Okay, and just tell me why do you want to give a name for those vectors. So that's for homework 3. Okay, homework 3. Question? Just use a data set, and I can use R code or M+ code. You can decide which software you prefer. And then conduct the EFA. Remember, that's for EFA. This homework is for EFA, not CFA. So that means in the very beginning, you don't know what's a structure. Okay, you're trying to discover the structure. What's K? Why do you want to choose that K? What's your factor structure? Okay, what's a factor lambda matrix? And name those vectors. Why do you have those names? Okay. Let's do next week before class. What do you mean? So next week is spring break.
Mm-hmm.
Okay, then let's do after 2 weeks. Okay, so you have enough time to finish homework. And then you also have homework in class. So that's good. Okay, two homework assignments for 2 weeks. Okay, any questions? Question? Good. Okay, let's have a break. And I'm sorry. Next session, we will have some other advanced techniques. For example, time series. These are all for for factor models, but different techniques. Higher order factor structures. Okay. So let's have 15 minutes break. Okay. Okay. So let's look at the higher order factor models. So we talk a lot about factor models. Actually, all of these are first order factor models. Just have one layer of those factors. So the diagram of first order is quite simple. So we have some observed variables here. So these are y1, y2, y3. So we have a lot of observed variables here. Yp. Okay. And then we have some, for example, these three are, okay, I think 1, these are F2.
These are like our
We
latents.
have a lot of FK, so we have a lot of variables here. And these might be correlated if they are not orthogonal. Okay, so these, if they are correlated, then we may have these correlation among these vectors. And of course, the variance of these vectors could be wrong, could be fixed or wrong, or yeah, you can identify the vector Lothian and wrong. So either way, and we have some variance here. And all of these are lambda values. And of course, we have the residual for first variables, and we also have the variance for the residual. Okay. The unique part, these are different than the unique variance. These are side part. All of these are side part. We have a lambda and the phi part. Okay, phi part is the pairs diagram for vector model. Okay, it's very common vector model. Now we are going to have higher order vector model. So basically, suppose I can have another layer of vectors. So this is for this general vector. We can just call it vector. This will influence all of the first order vectors. Of course, we have some higher order vector lambda values, and we have the variance of the general vector field. So in this case, it's called a higher order vector analysis, and we have different pieces.
How frequent are these? The higher orders? Like, is
That's a
this,
good question. You know what? If it's 2 layers, it's still okay. But if you have more than 2, the third, a lot of software cannot handle this case. So it's not very common. In most cases, we just use the the first order vector model. Sometimes, so this is another, yeah, these two are all second order vector models. This is third order, so this is not so common, but these, sometimes we have these vector models. That's a good question, because when you do the estimation of a lot of unknown vector loadings and side part, it's not so easy because everything's unknown. So all these are unknown. So
what's the best software to do something like this? Would R be able or Amos?
R is quite powerful. But of course, M+, yeah. Yeah, I cannot tell Lavon M+, which one is better, maybe M+, maybe R. I don't know.
R is the only
Yeah.
R and Jump are the only two I've used.
So here we have the 4 factors, okay, and we don't have anything above that. So it's called just first order, 4 factor model. We have 4 factors. So here we have second order. So above this first order, look at these are all circles. So that means these are not indicators. These are not variables. These not observed variables. Those are latent variables. So B here is second order, a single factor model. Okay, here finally we have single factor here. A second order. Here we have 2 factor model and the second order. Okay, so we have first order 1, okay, second order, first order here, second order here, and we have 2 factor model. And here, this is single factor. So finally, we have 3, okay, order 1, okay, first order, second order, third order. But finally, we have 1 factor, 1 single factor. It's called single factor, but 3 order, okay, 3 order. Yeah, I said, okay, so in reality, the order cannot be too high, okay, because the computation ability of software is so limited. So for 3 order, I try to have a model 1 through order, but the result is not good. So second order is good, okay? So not too high, okay? Not too high. So this is another concept, okay? So some people, if you read some articles, some people will mention bifactor. Bifactor is not a higher order factor. So let me give you the comparison, okay? So this is the one case. So we have observed variables here, a lot of items, or test. We have first order factors here. We have 1, factor 2, factor 3. Based on these factors, we have a higher order factor G. This is a higher order factor. Okay, but look at this. Okay, again we have a lot of items. Okay, those are observed variables. When we have one factor here, this is only one factor, single factor. When we have some other factors extracted here, So this case is called a bifactor model. It's not higher order factor model. This is called a bifactor model because in one way we can have this factor model, we can have a single factor model. In another way, when we have here, we have 3-factor model. Okay? So this one is called a bifactor model. It's different. These two cases are different. So don't get confused. Okay, they are actually mentioning different path diagrams. It's different. So we have this example. Okay, so we have spatial ability, verbal ability, memory ability, speed ability. So previously we just have this case. We have 19 tests in total. Suppose now, okay, I assume among these 4 cognitive abilities, there's a 1 general intelligence ability. That in charge of, okay, verbal or speed or spatial or memory ability. So that one is called G, general intelligence. So this is a second order factor. Okay, so this gonna influence these 4 first order factors, and these first 4 first order factors gonna influence those corresponding tests. Okay, so in this case, we have the second order factor model. So let's just try to do the exercise. We have the data set. It's an older data set. Okay, we use that for the model. Yeah. Now we only need to add a little bit of things. So we can just go to the PLC and please download the code called factor analysis 2. No. CFA higher order. Okay, CFA. Perform the factor analysis higher order, and the data set is a housing data set. So we have, suppose, okay, in the very beginning, we're going to change our working directory. And then we have our data available. So we're going to reading our data into R. And we can, at the very beginning, we can check. Okay, we can check. We can take out. We can pick this 19 test and then check the simplified data. So that's it. We have 19 columns, 19 tests, and we have sample size here. We have the number of columns here. Sample size is 145, so you can check. You can check again here. And number of column is 19. Has the P here. So again, we're gonna try SEM package and the Lavon package. First, let's try to use SEM package. Okay, so SEM package. So if you have Lavon package installed, then you're gonna attach that package first, and then use SEM, trying to avoid some mistakes, some error message. So if you go to the Okay, so SEM package here. So my bone package is here. Yeah, it's already detached, so I can only attach SEM, choose SEM. Okay, so library SEM is available. Now we're gonna set up our model, specify our model here. So this is our model. So specify model, and we have all of these lambdas. We have 19 lambdas from lambda 1 to lambda 19, and in addition to 19, we also have, let me check, we also have some new lambdas. These are 19 lambdas, 19 tests. So for each test, we have one lambda. But in addition to this 19, I have a new lambda here, lambda 10, lambda 11, lambda 12, lambda 13. So we have 4 more. I'm sorry, 20. I'm sorry, 20, 21, 22, 22nd. Okay. 23rd. Okay, so I'm sorry. So we have 4 more lambda values in addition to 19. So here. So 19. But for this method, we try to, this is variance function.
This is basically your model, right? Showing
Yeah,
your
this is our
correlations.
model,
Yep.
so let me see. These are 19, so where the other factor lambdas? Here. Okay, so we add 4 more lambda, so we call it not lambda anymore, we call it G, okay, G1, G2, G3, G4. So these G's go to spatial, this G go to verbal, this G goes to memory, this G go to speed, so we have different lambdas. Different factor loadings on the second layer, okay, that second order. And these are beginning part. And we identify our model by fixing the variance. Okay, this is the variance of spatial. Okay. All the lambdas are freely estimated, but we fix the variance of the first order factor spatial at 1. Verbal variance at 1. We fix the speed, the variance of speed at 1. Fix the variance of memory at 1. So these 4 variants, making the variable variance are fixed at 1. Let's check the G. Also G, the general second order factor, okay, the variance of the variable G is fixed at 1. And then we're gonna estimate all of these factor loadings. And of course, we have some other residual variables. These are residual variables from 1 to 19. These are residual. Okay. 19 tests. We have 19 residual variables. That's it. This is the end of this model specification. We just add this part. Okay. We just add the second order factor loading part. That's it. And starting from the beginning to the pound sign, we just highlight, click, and run. Okay, so just set our model like this. And for SEM, you're gonna tell the function the covariance matrix. So you have the covariance matrix of the simplified 19 tests here. Okay, this is a covariance matrix. Then finally, we have all of these components ready. Okay, so this is our model, we just described here. This is our covariance matrix, we just calculated by COV. Sample size, n rows, okay? Everything is ready. And then we're gonna look at the model fit indexes, okay? Fit indexes, we're gonna check all of these indexes. And we have the summary. So let's just try to look at the results. Okay. So model high-square value, equals freedom, p-value. So GFI value, okay, here. GFI, actually it's not good fit, okay, it's 0.8, it's 0.8. CA is larger than 0.05. MFI 0.8, okay. MFI 0.9. Okay. All of these are listed here. And, that is for the residual part. Okay. Lambda 1 to lambda 19. All of these are lambda estimate, standard error, Z value, P value, and residual variance S1 to S19 are residual variance for the unique part. Okay, from S1 to S19. And we have the G, okay, second order loadings. These are second order loadings. G1, G2, G3, G4. It's an explanation of all of these parameters. So finally, we have the result, I have the result here, okay? That's for this diagram, okay? And let's go back to R. We can also use a Lavon package. That's SEM package. Okay, so if we try to use Lavon, please detect the SEM package first. So you're gonna uncheck the SEM package and choose Lavon and check Lavon here. So it's just like detach and elaborate. And Lavon's the syntax is really simple. Okay, so we have 4 first order factors. And by using the equal sign tilde, we define these 4 first order factors. And each of these are measured by their corresponding tests. Okay, so spatial measured by these 4, verbal measured by these 5, speed measured by these 4, memory is measured by these 6. In addition to the first order factors, we have second order factor G is measured by these 4 first order factors. That's it. Okay? And of course, you should use code to include everything. That's your model. Okay? That's your model. So highlight the model here. Include everything, pick one to make your model ready. Okay. And we're gonna use CFA and the Lavon package to do the CFA analysis. Okay, this is your model, the name of the model, And we're gonna do set vector analysis model. Okay, so this is a simplified data set including 19 tests. Here, you're gonna tell which method to identify the model. In this case, you're gonna fix the variance of the latent variables at 1, okay? So it's true, then all the variance of the latent variables are fixed at 1. So try to highlight this part and click on results reported here. And at the very beginning, just add some information. And estimates, okay. Those are lambda values. The spatial is measured by these 4. So these are 4 lambda values. 4 lambda values, and the error Z value probability. And the verbal, we have this 5. Speed for memory, we have six, and here, this is second order factor loadings. G is negated by these 4, then these are second order lambdas, z value, standard error, z value, and probabilities. And these are residual variances, okay? Unique variances. The variance of the unique variances of these 19 tests. Estimate, standard error, z value. And all of these, the variance, okay, variance of the first order and the second order factors are fixed at 1. So you don't need to do any estimation here for them. Fit measures. Okay, so all the modified information are reported here. Number of parameters, okay, 42. Aspect value, degrees freedom, p-value, and CFI, TLI, NFI, RFI, RFI, PNFI, NFI, all of these are recorded here. SEA. Okay, so that's a advanced analysis result, and I copied them together, make a comparison. So we have the results here, reported here. Okay. So you can just compare the results obtained from different packages. So the estimates, okay, for spatial, verbal, speed, memory. Yeah, so this is memory. This is memory. This is memory. And this is speed, so they choose the order. This is for speed, okay? So you can tell the numbers are the same, except the rounding errors. So we have some rounding errors. Standard errors, ratios, probabilities. So either way, you can use SEM package or you can use Lavon package. The results are the same, okay? The results are the same. Okay, we just talk about higher order. Now let's look at another. So another tactic in the whole family. Factor analysis is a whole big family. So let's look at the data information first. A data set or data point has different dimensions. For example, different time points or different measured occasions. We may have time point 1, time point 2, time point t. Okay? We have different participants, okay, individual 1, individual 2, individual 2n, okay. We may have different variables, variable 1, variable 2, okay. All of this information combined together, we have one data set. Okay, so if, suppose if it's a cross-sectional data, cross-sectional, the time point is fixed. There's no variable for time points. So for cross-sectional data, we usually have multiple participants, multiple individuals, okay, multiple variables. For each individual, we have different tests, okay, different variables. But time is fixed, so that's for cross-sectional data. But if we have time series data, when we talk about a time series, actually, it focuses on single object or single participants. Time series, okay, so it's different time points, but we collect them from single object or single participants. And usually we have multiple variables and also multiple time points. So that's for time series data plus section data. So for different types of data, so we may have different constraints on these dimensions. So different types of data use different techniques to do analysis. Let me show you this table. Okay, this is a table. Tells you different techniques. Traditionally, we have R techniques. So this is just our traditional factor analysis. So the factor model is about variables. So we have different P variables. And we have different participants during our analysis. Okay, so different variables, repeated mode is different participants or subjects. How's the model? So usually for the traditional factor models, So the constant model is a fixed. The fixed variable is on 10 points. Okay. But we do have O technique, P technique, Q technique, S technique, T technique. Okay, by looking at different parts of these three components. So P techniques, usually this is for time series, P techniques. Okay, so we have different variables collected from a single participant. Okay. Here, we have single participants. These are different time points. Okay, repeated model, different time points. Occasions, we have different occasions or waves of data. Okay, and the constant is a fixed part. Is the individual is fixed. We have different variables. So this is time series, and we call it P technique. Okay, so previously we all look at R technique. So we also have O, Q, S, T. Yeah, so let me give you a detailed example of cross-section data. Cross-sectional data here, we mentioned the multiple objects, multiple participants, okay, multiple variables, multiple items or tests. Okay. So time is fixed. That's for cross-sectional data. So usually the data form will have have this format. We have different participants. We have different individuals. ID1, ID2 to IDN. Okay, sample size suppose is n. And for each individual, for each participant, we have variable 1, variable 2, variable p. We have p variables. And the time points is not considered here. We usually fix the time points, so we don't have any time points. So all the variable, all the values inside this table, we have this notation, ij. Okay, I means individual, different individual I. J is variable, different variables. It's a verbal test, or it's a math test, or it's a spatial test, something like that. We have different notations. Wide format is. And we use R technique. Okay, so this is called R techniques for cross-sectional data. That is our model. Okay, that is our model here. And suppose we have six variables. We have k equals 2. It's just like, let me just erase it and we can have a new. Suppose we have 2 vectors. So k equals 2. We have 6. Observe the variables. And it's quite simple. So everyone should have the path diagram like this. Okay, so we have 6. Observe the variables. Okay. Y1, Y2, Y3. 6. Observe the variables. And k equals 2. That means we have 2. Which in fact, suppose, okay, F1 gonna inference these 2, I'm sorry, these 3, and F2 gonna inference these 3. Okay, that's a path diagram for, of course, we have that's a path diagram for R technique. R technique. So this is our traditional method. Now let's look at the time series data. Time series data focus on single individual. So for the single participants, we have different time points. Time point 1. Okay, first, for example, day 1, time point 2, day 2, day 3, day 4. So we have different time points. At each time, first day, we have variable 1 obtained, variable 2 value obtained. We have variable p value obtained. So we can use ytj. Y is observed. Observe the value here. T is different time points. Okay, different time points. Time point t. J, different variable. Okay, ytj is a common format for time series data format. Then we also have that model. Okay, so yt lambda ft plus et. So suppose we have okay, it's quite the same. We only need to change it's quite the same. Okay, so we have 6 variables. Okay, at each time we observe these 6 variables. So this is a speed test. Okay, this is maybe a verbal test. This is a math test. This is another test. Okay. Each day we have these variables collected, and we assume that we have 2 latent factors. That's it. But all of these are collected from single participants, not multiple individuals, just single participants. But we have different time points. Okay, time point 1, time point 2, time point 3. Let's look at the example. So this is also a very famous data set. The data coming from a woman, a lady. Okay, so actually she just had a baby. The data coming from before and after delivery for 103 days on 6 variables. So active, lively, happy, sluggish, tired, weary. So these 6 variables are collected from the single lady, and it has 103 days. So
would that be considered long enough to be longitudinal data for 102 days?
Longitudinal and time series is different.
Okay.
Longitudinal have a bunch of people.
Okay.
And series only have 1 people.
Okay.
Yeah. So all of these. Okay, yeah, that's 103 days. Okay. Here we have 100, and actually we have 101, 102, and 103 days. Okay. And this is an active variable. Okay, so sometimes it's 1, sometimes it's 2, sometimes it's 4, okay, sometimes it's 0. So that is a variable across these 103 days. This is another variable. This is a third variable. This is a fourth variable. Tired, weary. Okay, so for example, weary, we have 103 time points. And each time point we have different values. Okay, 6 variables. Yeah. Actually, these 3 are influenced by positive effect. These 3 are influenced by negative effect. So we consider there are 2 latent factors. One is positive effect, or one is negative effect. And the positive is measured by these 3, and the negative is measured by these 3. Okay, so we have 6 variables. And we can do difference analysis. Okay. So we can just, I have the data and I have the code. So if you go to the ELC, download the factor analysis 2 P technique. Okay, that's it. This is our code. P technique, time series. And the level data. So first, we can just repeat the level data here. It's called the level. The data set is called the level. And you can just look at the level here. That's the data set. Of course, this is the beginning part. Okay, this is the head. The 6, the previous 6 rows. First day, 1, 1, 1, 2, 1, 1. It's quite stable. Okay. Oh no, it's 1 means low. Okay. All of these are low. So on the first day. Second day, 3, 3, 3.
The drugs were still kicking in.
Yeah. Second day, it's quite a positive thing. Okay, all of these are 3, but for negative, so we have 0, 1, 1. So third day, it's quite negative. All of these are 1, 1, 1. Okay, but sluggish, tired, weary, 3, 3, 3. Okay, and the fourth day, fifth day, sixth day, all of these are quite positive, not negative. Negative scores are quite low. So that's a data. And then, we can check the rows. Okay. 103. Okay, 103 days. In total, we have 103 rows. Suppose, yeah, so let's try to use different package. Suppose we use SEM first. So if we use SEM package first, I'm gonna make the SEM available here. And calculate the covariance matrix of this level data. And trying to set up your model, like, okay, this is your specified model. So suppose I have PA, positive effect. PA gonna influence active, lively, and heavy, these three variables. We have lambda 1, lambda 2, lambda 3. And the negative effect, sluggish, tired, weary, we have lambda 4, 5, 6. And then fix the variance of PA and NA at 1. But I'm gonna investigate the covariance. This is the covariance between, or correlation between positive effect and negative effect. This is a parameter. I'm gonna estimate this parameter. Okay, starting values and NA. And some residual variance. All of these are residual variance. Okay, all of these 6. So that's my model. So try to highlight all of these statements and run. And look at the results, okay? Look at the results. Oh, something wrong here. Did I miss something? I didn't specify the number of rows here. Okay, so I have to run the number of rows here. Then I rerun the code. Still, level residual not found. Let me see, did I miss something here? Level S. Level S is here. And levels angles. String. Just again. Now it's working. Okay, so I missed some lines, so I didn't work in the head. So let's look at the results. Model information, it's quite good. Okay, so all of these FI is very close to 1, Okay. IMSEA. Oh, this one's quite high actually, larger than 0.08. And this value is also low. Yeah. So some numbers are good. Some numbers are good, for example, these, but some numbers, for example, this one and this one are not good. So you can say that maybe this is not a very ideal model. Didn't provide a very good model fit analysis. So let's look at the estimates. So all of these are factor loadings, and this is the correlation. Okay, that's good. Okay, that's good. This is a covariance between the positive and the negative effects. It should be negative because positive, negative, it should be negative. This is negative, and negative 0.8 is quite high. It's quite high. That makes sense. And all of these are residual values. Okay. And let's try to look at the Lagrange result. detach lesson and use level package. Now let's look at the code. The code is quite simple. We have two rows. That's it. We have factor positive effect, which is influenced by these three. Factor negative effect, which is influenced by or measured by these three. And we have this CFD model. The results are the same. Okay, RMSEA is 0.1. We cannot change the model fit indexes because the model is the same, the data is the same. We just use different packages. So the results should be exactly the same, except some rounding errors. Okay. So we hope that these are. Oh, okay. So here we use different model identification method. We fix the first factor loading at 1. So it's different because we use different model identifications. So that's why if you look at the covariance here, okay, it's different. Now it becomes 0.681. So if you want to make that exactly the same, we're gonna add this option. Let's see.
Bless you.
Option of this one, okay? So if we have this option, then the results will be different. Now the covariance, okay, it's negative 0.8. And all the lambdas are freely estimated. Okay. In this case, it's just the same as the previous analysis. And all the model fit indexes, of course, all of these are same. Okay. These are exactly the same. So we're trying to use R code and Lavan code to do the data analysis. Actually, this is a famous paper. So the first author is a husband. The second author is his wife, because the data coming from his wife. Yeah. So it's good to provide the data for husband and wife. At least she has the second author. Okay. It's a highly cited paper. Yeah, she just provided the data of 103 days.
That was both faculty?
No, I think the husband is a faculty.
Yeah.
Oh, really? Actual participant.
Yeah. How's that not a bias?
And they just had a baby. That's a good thing. Yeah. So let's have a summary. So we did the EFB and we also did the CFB. Those are steps. So for your homework, okay, this is for your homework 3, homework 4. Okay. So you're gonna follow these steps to do the CFB, EFB, and CFB. So homework 4, the same data set. For homework 3 is for EFB. You're gonna decide the number of factors and the factor patterns. Now homework 4. Based on your EFA results, now you fix the number of factors. You fix the factor structures. Please run CFA. This time is for CFA. Oh, I'm sorry. This is
that should be 3.
Yeah, I'm sorry. Yeah, homework 3. Homework 3. Yes. And then CFA. We assume that there's no cross-loading. So that means you cannot have these cross-loading, okay? You cannot have these cases. You cannot have these cases. So just as, yeah.
single factor for
Yeah,
each
just
of those.
assume that there's no cross loadings. Just keep it simple. Keep it simple.
Homework 4 is actually on the 21st, correct?
Homework, which one for?
Or they both do it on the same day.
Because it's spring break.
Uh-huh.
So after 2 weeks, you're gonna have homework 3 and homework 4 due.
On the same day.
Same day.
Okay.
Yeah, you just combine these two together, and after 2 weeks, you submit both of them.
And then only one homework left after that.
Yes. Yeah. And the project, and that's it.
Oh, that
Okay,
project's
so-
a nightmare.
Okay, so CFA without, suppose there's no cross-loading, then just run the CFA. And then tell me, okay, why should we identify the model? Okay, we have different methods to identify the model. Why? Okay, just tell me your reason. Which identification method did you use? So did you fix the variance at 1, or did you fix the factor loading at 1? Okay. But show me the reason why we should identify the model, factor model. And you can also look at the model fit indexes. Tell me if the data fit if the model fit the data well or not. Okay. So 3 parts for homework 4. Yeah. So after 2 weeks, on March 14th, the homework 3 and homework 4.
So our spring break is going to be spent doing your homework.
It's quite simple. Okay. So any question? Question?
I have a quick question.
Yeah.
Can you explain what you mean by identify the model? Like what do you mean?
Identify models that, okay, so actually we have slides to talk about this, or you can just check the chapters. So the book chapters talk about the model identification clearly. So let me see. So that's from, let me see. It's for CFA. I think it's here. Model identification. This is second part. This is yes, this is yes. When did we talk about it? Here, this is the model identification depth. So the factor model cannot be identified without constraints. The factor are unmeasured and thus have no scale. So we're gonna identify model. The factor have to be given some specific scales, okay? Because all of these are unknown. So we have to fix something to make a scale. Okay?
I see.
Yeah.
Okay, that was like some theoretical
Yeah.
reasoning, but
We
not
can, yeah, you can also look at the book chapters. So bronze, this is for CFA. So CFA, this is for the one. There's a bonus book. Bonus book, did I upload with a bonus book? Wrong. Analysis. My bonus book. Confirmed effect analysis, chapter 7. Yeah, you can just look at this chapter. They include a lot of topics. First, I mentioned Jeffrey. Yes, matrix. Identification. Yeah. Identification, this part. And the follows chapter 7. Yeah, you can just read through this part and have some feelings. Yeah, good. And any other question for homework 3 and 4? Okay, then that's it. That's for our today's class. Thank you. Yeah. Homework 2 is due to if you upload it to VLC, that's perfect. Okay. Thank you. I'm gonna see you in 2 weeks. So happy spring break.
We have what, 6 classes left?
What?
So we only have what, 6 classes left? We're over halfway, aren't we?
Like next term, I know.
8 classes left, okay.